So, our next topic, topic 2, will be chemical kinetics. Now, remember that these videos are intended to be for revision, or perhaps sometimes if you wanted to view ahead of the lecture. These are not intended to be a replacement for actually attending the lecture, but rather to be used as a companion type resource that you can then use if you wanted to revise over the lecture or anything like this. But let's get started on chemical kinetics. Okay, so here we've got on this slide, you can see we have some reactants and some products. Okay, reactants and products. Now, there's an initial state and a final state, and we know that reactions have different rates of reactions. Okay, so they can proceed at a different speed, and chemical kinetics is concerned with this rate of reaction. It's all about how fast does a reaction proceed. Okay, and there's many different ways of monitoring a reaction. So it's particularly easy to monitor a reaction where the product is coloured or has a UV absorbance, okay, or a visual light absorbance that we can then use to monitor the production of our products. Okay, but there's many different ways that we can actually measure this. But the point is that chemical kinetics is concerned with how fast a reaction proceeds. It's that simple. Okay, obviously reactions are going to take place at a different rate under different conditions. So if we change the temperature, if we change the pressure, if we change the solvent, even the presence of light can then change the rate of the reaction. So we have to keep the conditions constant when we're measuring a reaction rate and when we're comparing different reactions. Okay. Also, as well as just the rate, chemical kinetics also helps us determine the pathway via which a reaction proceeds. So by having a look at the rate and how the different concentrations of reactants actually affect the overall rate, we can then get an idea of the pathway via which a reaction proceeds. So it can give us information about the reaction as well. There's 3 key aspects that we're going to have a look at. There's the collision theory model, reaction mechanisms, and also rates of reactions and rate laws. Now, the collision theory model is exactly what it sounds like. Okay, so in order to react, these molecules, they have to collide with each other, and they have to do this with the correct orientation and enough energy for the reaction to proceed. So if you imagine all of your reactant molecules, they're in a solution or they're in a gas perhaps, and they're all moving around. Okay, how can we change the speed at which the molecules are moving? Well, you could perhaps heat the reaction, and then they're going to move faster, okay, and they're going to gain energy. Also, in the collision theory model, we can have a look at the activated complex, what's called the activated complex, and there's a slide very soon where we'll have a look at this, and also activation energy and what this means. So what energy barrier has to be overcome for the reaction to proceed. Okay. Also, reaction mechanisms. So we've already had a look at some mechanisms in this course, but we know that a reaction mechanism is a series of steps via which a reaction takes place. And for a mechanism to be valid, 2 conditions have to be met. So the steps of the mechanism have to add to give the overall reaction, and the rate law for the overall reaction must be the same as that of the slowest step. So in other words, this is the rate determining step. So if there is a particularly slow step in our mechanism, the rate of this slowest step is going to determine the rate law for the overall reaction. Then we'll have a look at rates of reactions and rate laws. So this is a quantitative approach to produce a model which can then be used to determine the rate for a particular reaction under certain conditions. So we're looking at the numbers, okay? This is when you're taking experimental data, so you're actually going to do the reaction in the lab, or you're looking at data that's been gained from having done the reaction in the lab. And from this data, we can determine the rates of the reaction. And it's actually quite easy to do, so don't let this, you shouldn't feel intimidated as you're approaching this, because it's actually very, very simple. And it's so simple that some people actually get stuck on that point. First of all, let's have a look at collision theory. So molecules have to collide in order to react, and they've got to collide with the right orientation and enough energy. So here's a diagram that shows, now we've got some NO2, okay, where we've got a system where we've got on the left here before the reaction, and on the right hand side we've got after a few of the NO2 molecules have reacted. Okay, but the point is they have to collide with each other in order to react. You can just imagine them bouncing around in the container. So these are a gas, right? So this is a gas molecules bouncing around inside the container, and the actual molecules have to collide for our reaction to proceed. Now, we need enough energy. So to get an effective collision, we need the right orientation, but we also need the right amount of energy as well. And this is going to be related to the activation energy to produce the activated complex. Now, you can think of the activated complex as being a little bit like a reaction intermediate, okay, where it's only transient in nature. It's not particularly stable, but it's the complex that needs to form in order for the reaction to proceed. And in order for this complex to form, we need a sufficient collision. And you can see here the activation energy is given by EA. So the symbol here is EA, activation energy. And in this example, 10.5 kilojoules per mole of energy is required for this reaction to proceed. And you can, if you follow the progress of the reaction, you can see there's a little hump, if you like, activation energy hump for the reaction to proceed. So this little bit of energy needs to be overcome for the reaction to proceed and to produce the products. And you can see in this case the products are a lower energy than the reactants. Okay, now in order for the reaction to proceed though, we still need to overcome this amount of activation energy to form the activated complex. Actually, just back to this slide again for a second, you can see there's something else on here, delta H. Now, we may not talk too much about this today, but this is going to be important later on. So this is our change in enthalpy. And this is something that we can look at to determine whether or not a reaction will proceed. You can propose a reaction, but will it proceed without a lot of encouragement? Okay, if we were to mix these chemicals together, mix these molecules together, are they going to react? And the change in enthalpy, or delta H, is something that we can look at to help us work this out. But we won't talk too much about that today, but we'll cover this very soon, actually. Now, the correct orientation is important. So here's a diagram illustrating how important this is. So if you get the correct collision geometry, okay, so we need the oxygens coming together in this case. So this reaction, we've got some NO and some O3, okay? They're going to collide together, and we're going to produce some NO2 and some O2. So we've got nitrogen monoxide and some ozone, and we're going to produce some nitrogen dioxide and some oxygen gas. So we need the oxygen atoms to collide with the nitrogen for the reaction to proceed. If the oxygen atoms collide with another oxygen atom, then we're not going to have the reaction proceed. So we need the correct geometry as well. Now, why is this important? Well, this actually explains why, in the case of enzymes in biological systems, these can actually be used by biological systems to speed the reaction significantly, and they greatly lower this activation energy, if you like to think of it this way, where the two parts are aligned. So the enzyme literally takes the two molecules that are going to react and it puts them into the correct orientation, so they get the correct geometry, so the reaction proceeds at a much greater rate. So what can affect reaction rates other than enzymes, okay? So an enzyme is a type of catalyst, So the nature of the reactants, so the types of bonds, the polarity, the shape, the size. The concentration of the reactants is important. Obviously the rate depends on the concentration of the species involved in the reaction. Generally the more concentrated the reactants, the more collisions that you're going to get per unit time, and the faster the reaction. You can express the rate in terms of the loss of a reactant or the production of a product. So you can get either a positive or a negative term depending on what area you're looking at of the reaction. Okay. Surface area is important. So remember the nylon synthesis experiment. So we've all done the nylon synthesis experiment by now. There was a certain surface area between the two layers, between the two reagents. So imagine if you had a very narrow beaker or even like a cylinder or maybe a very tall test tube, you're going to have less surface area between those two layers for the nylon to form. Whereas if you did it in a very large size beaker, you're going to have a larger surface area, okay, and you're going to have a faster reaction rate. You're going to be able to produce more nylon more quickly. Or another example might be if you've got a solid reagent in a liquid reagent, and that solid reagent you might put that in there in one big lump. So perhaps we're going to react some iron metal, okay, a metal catalyst, or maybe some zinc. We're going to put a big lump of zinc in there into some hydrochloric acid, or whatever our reagent might be. Now instead of putting in a big lump of zinc, we might chop the zinc up into smaller pieces. That's going to increase the surface area, or we can even make it into a powder, pulverize it into a powder, and we're going to get a much greater surface area, faster reaction rate. Okay, so here's a video that I've prepared to demonstrate this example. If we put the large solid into the liquid reagent, we'll get a slower reaction. So this might be like our lump of zinc or whatever it might be into our liquid reagent. It's going to react slowly. But if we were to pulverize this and make the particles smaller, make it into a powder, and we then put this powder into our liquid reagent, what we might find is we get a faster reaction, and here it comes, bang. Okay, so we've got a faster reaction now, and the conclusion is that surface area can affect the reaction rate because those smaller particles are going to have a greater surface area. Also, catalysts, this can include enzymes as well, and temperature can affect the rate of a reaction as well. So we know that from when we learnt equilibrium, that temperature can affect the equilibrium position, okay? But temperature can also affect the rate of reaction, so how quickly the reaction reaches that equilibrium position. We know that, for example, don't get confused, because we know that a catalyst won't actually change the equilibrium position, but it will change the rate. So we're just looking at reaction rate now, okay? Temperature will affect reaction rate, catalyst will affect reaction rate. Let's have a look at how we can describe the initial rate of a reaction. Okay, if we take a simple reaction where we've got A of A plus B of B gives us products. Now, the small a and the small b, these are coefficients. It might be a little while since we've looked at coefficients, but remember that coefficients are these numbers out the front that tell us how many moles or mole equivalents we need of A and B in our reaction. So what we do to describe the rate is, here's the expression, the differential rate law, K multiplied by concentration of A raised to the power of A, which was the coefficient of A, and the concentration of B raised to the power of B. Now, A and B are reaction orders. Okay, so here A and B are reaction orders. Now, these have to be measured experimentally, and we'll cover this a bit later in the lecture. Now, it's true as well that these can correspond to the coefficient out the front, but this is only for the elementary reaction, and again, this is, well, maybe not again, but maybe this is the first time you're hearing this. This is for the elementary step, and we'll cover what all of this means later in the lecture. Okay, let's have a look now at average rates of a reaction. Now, the average rate of a reaction is measured over a certain time period. Now, this might be a very short time period, or it might be a long time period. Okay, it depends on what we actually want to look at. Now, the speed of the reaction, which is its reaction rate, is the concentration of the reactants or the products per unit time, and the units are moles per litre per second. So obviously the reactants are going to decrease in concentration over time, and the products are going to increase in concentration over time. Okay, so the concentration of A and B in this case are going to change with time. Now, in this case, we can express the rate of this reaction as the disappearance of A, which is going to equal the appearance of B, because it's a very simple reaction, because A is becoming B. There's no coefficients there out the front. Okay, so as the concentration of A decreases, the concentration of B will increase by the same amount. Now, to work out the average rate of disappearance of A per unit time, it's given by the change in the concentration of A divided by the change in time. So we have to look over a time period. Okay, and you can see in this example we've got our 3 flasks that have been charged with 2 gases, and over time we've got a reaction. So at 20 seconds we can see the reaction has proceeded somewhat. So starting with 1 mole of A, now it's only 0.54 moles of A left, and after 40 seconds there's only 0.3 moles of A left, but we have to look at our time period. Okay, so moving along, depending on our time period, we can get a different value, because the concentration as it changes over time is not going to be, in most cases, a linear relationship. In a lot of cases, it's not going to be a linear relationship, so we have to look over a certain period of time. Now you can see in this case, the concentration of A is dropping quite sharply at the start of the starting time, okay, at the start of the reaction, and then over time the decrease in A is less and less and less and less. And this is quite obviously because there's going to be less concentration of A in solution, or in the solution of gas, over time. So the reaction rate is going to decrease over time. But to determine the average rate, we have to look over a time period. So here's a tabulated version of the example that we were just looking at. So we've got the concentration of A here in the column in the middle, and the concentration of B over there on the right hand side, and you can see the time periods there on the left column. So after 20 seconds and after 40 seconds, how they've changed. So remembering back to the example, we had red spheres and blue spheres that were representing our different amounts of gas of A and B. Okay, it was actually 1 mole and 1 mole of both, regardless of what it says there. Okay, so for the reaction of A to B, we need to determine the average rate of appearance of B over the time period 0 to 40 seconds. So notice in the question here we've been given the time period. If we're not given the time period, it's difficult to determine the average rate. But if you're told to determine the average rate and you're not given the time period, assume that it's going to be over the entire reaction. So right from the start to right at the finish. So this is over the 40 seconds though. That's the longest time period that we were given. That's not necessarily the end of the reaction in this case. Okay, so our rate is going to be our 0.70 minus 0. Okay, so after 40 seconds we have 0.70 moles, well in this case moles per litre of B appearing over time, minus 0 moles per litre at the start of the reaction, and the time is 40 seconds. So 40 minus 0 is our time period. Okay, so we get 1.75 by 10 to the minus 2 moles per litre per second. So that's average rate of change, or average rate of reaction. Let's have a look at the instantaneous rate of change. Now this refers to a moment in time. Okay, so the actual rate of the reaction is going to change with time, and the reason why is because we're going to have a decrease in the concentration of our starting materials over time. Now we can use a graph to help us determine the instantaneous rate. So if we have a look at the slope of the line at a specific time t, we can then get the instantaneous rate at any point during the reaction. Okay, but we have to then have a look at our slope at any time point. So for example, we can see here we've got two rates Okay, potentially the rate could be calculated at t equals 0 and perhaps t equals 600 seconds for this reaction, and you can see that the slope is actually quite different in each of these cases. We won't go too far into that. Okay, so if we consider this reaction, have a look. We've got 2HI gives us hydrogen gas and iodine gas, and you can see we've got the 2HI. So what's happening is that HI is actually disappearing at twice the rate of the appearance of either product. What that means is that for every mole of hydrogen gas that's formed, we're actually using 2 moles of HI. So if we're looking at the rate of the reaction just by looking at the disappearance of HI, it will seem to us as the observers that the reaction is actually proceeding at twice the rate that it really is. So what we do is that we divide the rate of the disappearance of HI by 2. Okay, so the rate is now given by half of the change in concentration of HI over time, which is the same as the change in concentration of hydrogen over time, which is the same as the change in concentration of the iodine gas over time. Okay, but we just have to halve that first one, halve the concentration of HI over time, because otherwise it will appear as though the reaction's actually proceeding at twice as fast as it really is. So what we do is we put 1 on the coefficient. So for the general reaction, A of A plus B of B gives us C of C plus D of D. It's going to be 1 on the coefficient, so 1 on A multiplied by the change in concentration of A over time equals 1 on B times delta B on delta T, and so on. So we have to go 1 on the coefficient. So this is where stoichiometry is important in rates. So here's a concept checked. So the decomposition of N2O5 proceeds according to the following equation. So 2 N2O5 gives us 4NO2 plus O2. Okay, so if the rate of decomposition of N2O5 at a particular instant in a reaction is 4.2 by 10 to the minus 7 moles per litre per second, work out the rate of appearance of NO2 and O2. Let's have a look at what our expression would be. Okay, so working with the coefficients, we know it's going to be half the change in the concentration of N2O5 over time. It's also equal to a quarter of the change in the concentration of NO2 over time. It's also equal to just 1 times, or because there's no coefficient out the front of the O2, so the change in oxygen gas over time. So that 4.2 by 10 to the minus 7 moles per litre per second, that's the rate of decomposition of N2O5. Okay? Now, we know that we're going to have to divide that by 2, aren't we? Because that's the coefficient in front of the N2O5. So we know that the rate is actually half of that. Okay? If we're looking at, for example, oxygen. So to work out the first part of the question, consider that the rate of the disappearance of N2O5 is 4.2 by 10 to the minus 7. That means that the rate of appearance of NO2 is going to be, well, double that amount, because NO2 has a coefficient of 4. Okay, so it makes perfect sense if you look at the reaction. So we've got 2 N2O5. That's corresponding to 4 NO2 on the other side. So if the rate of disappearance of N2O5 is 4.2 by 10 to the minus 7, then we have to multiply by 2 to get the rate of appearance of NO2. There's going to be twice as much of NO2 appearing over time. So we get 8.4 by 10 to the minus 7 moles per litre per second, is going to be our rate of appearance of NO2. For O2, it's just half the original amount. So we probably could have worked out O2 first. It would have been a bit easier. So we know it's going to be half the original amount because that original amount, that 4.2 by 10 to the minus 7, is referring to the N2O5, and the N2O5 has a coefficient of 2 in the front, which means that it's going to be double the amount of the rate of disappearance if the coefficient wasn't there. So let's have a look at concentrations in the rate law. So just as we did in our lab, we can collect some data on the rates of reactions by altering the concentrations of one of the reactions. So we haven't actually done the lab yet, okay? But just as we will do in the lab, depending on when you're watching this video, we need to collect some data on the rates of reactions, okay? So if we know the rate law for a reaction and its rate for a set of reactions, we can determine the rate constant, which is lowercase k. So remember, uppercase K was our equilibrium constant. Our rate constant is a lowercase k, and the reaction orders M and N with respect to each reactant. Okay? So the overall reaction for the reaction, the overall order for the reaction is M plus N. We actually add them together. So here's our rate law. So the rate is dependent on the concentration of our ammonium ion, NH4+, plus NO2 minus, and that's going to be our rate law. So K multiplied by the concentration of NH4 plus to the M multiplied by the concentration of NO2 minus to the N. This is our rate law. K is our rate constant. So M and N are the orders of the reaction with respect to each reactant. Let's have a look at this example. Let's have a look at table 15.2. So for this reaction, we're going to do some experiments. Okay, so let's hold the concentration of NO2 minus constant for a start. Let's keep it at 0.2 moles per litre. Let's change the concentration of our NH4+. Let's change the concentration of our ammonium ion. So we'll start with 0.01, then change it to 0.02, then change it to 0.04, and we'll have a look at how the rate changes. Okay, and every time we double our ammonium ion concentration, we're actually doubling the rate. So 5.4 becomes 10.8, for example. Okay, this is the initial rate that's been measured. And similarly, when we hold the NH4 plus concentration steady at 0.2 and we change the NO2 minus concentration, again, as we double the concentration, we're doubling the rate. So that means that M and N are both first order. If doubling the concentration doubles the rate, then it's first order. Okay? If doubling the concentration has no effect on the rate, then that's zero order. So here's some examples of some different rate laws. So for the first example, that particular reaction, experimentally, it's found that the concentration of the NH3 gas has no effect on the overall order, so rate simply equals K. It's a zero order reaction. In the second example, it's a first order reaction because the concentration of our N2O5, our dinitrogen pentaoxide, affects the rate. So doubling the concentration will double the rate. Okay. You can also get odd numbers like 1.5, for example. Now, in the last, and this is because we've got a complicated reaction mechanism. That's the reason why we can sometimes get odd numbers. Okay, we won't discuss those too much. Usually we get whole numbers. Okay, so in the last example, H2 plus I2 gives us 2HI. Now the rate is given by the concentration of both the hydrogen and the iodine gas. So they're both first order. So first order in respect to hydrogen, first order in respect to iodine, but overall order is going to be 2 because we add them together. Okay. So the values of the orders must be determined by the experiment. You can't really tell this from looking at the balanced overall equation. Okay, and this is because a balanced overall equation may not be telling the whole story. So maybe there's more to the reaction mechanism than can be had by the overall equation. And we know that these reaction orders are actually coming from usually the rate limiting step, okay? So and we'll talk about that very soon. But the values of these reaction orders can give an insight as well into the mechanism of the reaction. So the reaction rate units depend on the reaction order. Okay, so depending on the overall order, we use different units. So in our previous example, we were using moles per litre per second. Okay, and this works for a zero order reaction when we're describing the rate. But the overall rate, if it's a first order reaction, we can say the units are per second. Okay, and if it's a second order reaction, it's per mole per second, and if it's a third order reaction, it's moles per litre to the -2 by seconds to the -1. So we're pretty much, in all of them, it's always seconds to the -1, it's always per second. Okay, starting with zero order, it's moles per litre per second, and then it's as if we're taking away a moles per litre, if you like, every time. This is a way of remembering it. So how do we determine the orders using experimental data? So in this example, you can see if we double the concentration of NO2 minus while keeping the NH4 plus steady, the initial rate doubles, and the same is true if we do the opposite. If we hold our NO2 steady and double the amount of NH4, then we double the reaction as well, which means it's first order in both the NH4 plus and it's also first order in the NO2 minus, so M and N are both 1, okay, which means the overall order is going to be 2. Zero order reactions is one whose rate is independent of the reactant or reactants. So the rate is equal to negative the change in concentration of the reactant over time, which equals the reaction rate constant multiplied by the concentration of our reactant to the power of 0. Overall, the rate is equal to the rate constant. So rate equals lowercase k, which is a rate constant. If we were to integrate this differential equation, we would obtain an equation which relates to the concentration of A, or concentration of reactant, at the start of the reaction to the time period that we're measuring. So the concentration of our reactant at any time equals our rate constant multiplied by that time plus the concentration at the initial concentration, sorry. So the concentration at any time equals the rate constant multiplied by the time plus the initial concentration. Okay, so we take our initial concentration and to that we add the rate constant multiplied by the amount of time. Now this form of the rate law is called the integrated rate law, and you can see why it's very useful. Using this rate law we can then work out how much of our compound we have at any given time based on how much time has passed. Let's have a look at first order reactions. So one whose rate depends on the concentration of a single reactant raised to the first power. So it's going to be the rate constant multiplied by the concentration of our reactant to the power of 1. And if we integrate and rearrange, now you won't have to do this from scratch, we get our form, so the natural log of the concentration of the reactant at time t equals negative kT plus the natural log of the initial concentration of our reactant, and this is in the form y equals mx plus b. So if a plot of the natural log of our reactant at any given time versus time is linear, then it's a first order reaction. Okay, so if we're measuring our concentration of our reactant over time, what we can do is take the natural log of that concentration and plot that against time, and if we get a straight line, if it's linear, then we can say our reaction is first order. Now this is really useful in a lab experiment, so we might be able to perform our reaction, take some measurements over time, and then make a graph. And if that graph is linear, then we can say yes, this reaction is first order overall. Let's have a look at second order reactions. So a second order reaction is one whose rate depends on the concentration of the reactant or reactants raised to the second power. Okay, and if we integrate and rearrange, now we find that a plot of 1 on the concentration of our reactant at any time versus time is linear, then that will be a, well, that should say second order reaction. Okay, so it should actually be a second order reaction. So you can see, again, this is useful. All we need to do is have a look at our two plots. It's very obvious if it's a zero order reaction, but because it's not going to have any difference, there won't be any change in the reaction rate if we're changing the concentrations. But if there is a change, we can plot our concentration over time. Okay, plot the natural log of our concentration over time, or we can plot the inverse of our concentration over time. And whichever one is linear is going to tell you whether it's a first order or a second order reaction. You won't have to derive this, so we won't be working with a lot of this kind of maths, other than knowing these facts, the differences between zero, first, and second order reactions. Let's take a quick look at half-life. So another convenient way to describe how fast a reaction is the half-life. A fast reaction will have a short half-life, for example. So it's given by T1/2, and it's the time required for the reactant to reach half its initial value. This is also used as well in drug uptake and also drug elimination from the body. So every drug has a half-life. So if you take, if the half-life of a drug is, say, 3 hours, and you take your dose of the drug, that means in 3 hours' time, half the amount is still in your system, and then 3 hours after that, half of that again, okay? And over time, it reaches insignificant amounts where the drug no longer has an effect. So it's also useful for radioactive isotopes. Okay. So the concentration of a reactant at its half-life, so that's what this AT1/2 is, we can determine the concentration of a reactant at its half-life by substituting it for half of the initial amount into an integrated form of the rate law. So for a zero-order reaction, half of the initial amount of our reactant equals negative kT T1/2, which is our half-life, plus our initial concentration. And then we can just solve for T, which is going to be our T1/2. Okay, so pretty much what we're doing is we're saying, okay, this is the amount we're looking for, which is half the initial amount, and that's going to be equal to negative kT plus the initial amount, where T is our half-life, or in this case we're calling it T1/2, which is our half-life. Okay, and we can rearrange that into another form where we say our half-life is equal to the initial concentration divided by 2K. So 2 times our rate constant. And we can do something similar for a first order reaction because we've got the natural log in our first order reaction, and you won't have to derive these yourself. Okay, you won't have to derive these yourself, so if you don't get too hung up on the maths, but because there's a natural log, what we can do is we can say that the half-life, if it's a first order reaction, is equal to 0.693 on K, where K is a constant. It's the rate constant. So for a zero order reaction, it's directly proportional to our initial amount, whereas for a first order reaction, it does not depend on the initial amount and it remains constant throughout the reaction. Let's move along to the Arrhenius equation. So Arrhenius noted that the reaction rate of most reactions increases with an increased T, which is temperature, but in a non-linear way. Okay, so the reaction rate generally increases when we raise the temperature, but this is non-linear. So K, which is our rate constant, equals our frequency factor, which is also a constant, multiplied by E, which is related to our natural log, to the negative, E is a constant as well, to the negative EA, which is our activation energy, divided by R, which is a constant, the gas constant, T, which is our temperature. Okay, so this is our relationship. And it predicts that the reaction rate decreases as the activation energy increases. That's the important part of this. So as we're making the activation energy larger, so notice that's negative EA divided by RT in the Arrhenius equation. What this means is as EA is getting larger, the reaction rate is going to decrease. So you can see in these three examples that we're starting with the same amount of potential energy in all three, and we've got some differences. So we've got some different activation energies, okay? And let's have a look at which one of these is going to be the slowest and which one is going to be the fastest reaction based on the activation energy. So based on that, we can say that the reaction with the largest activation energy is going to have the slowest rate. So let's have a look now at reaction mechanisms and how this relates to kinetics. So elementary reactions equal the steps of the mechanism. So the number of molecules that participate as reactants in an elementary step defines the molecularity of the reaction. Okay, whether it's a unimolecular, bimolecular, or termolecular, for example. And the chemical equations for the elementary steps in a multi-step reaction must add to give the equation for the overall process. So if the elementary step is simply A becomes products, this is unimolecular, so it's just one molecule. Okay, or A plus A gives us products, so this is bimolecular. Okay, same if it's A plus B, it's also bimolecular. 3 would be termolecular. Now the overall reaction isn't often an elementary step. It's normally just the overall sum of the elementary steps. We'll have a look at this soon. So let's recall that the rate laws for chemical processes must be determined experimentally. Every reaction is made up of one or more elementary steps. The rate laws and the relative speeds for these steps will dictate the overall rate law. We'll look at the reaction mechanisms that lead to rate laws that are consistent with the experiment. If we know that a reaction is an elementary reaction, then we know its rate law. It's based directly on its molecularity. Now, this is the thing, we don't always know if a reaction is an elementary reaction, and that's why we must perform the experiment first. If you're told in a question that it is an elementary reaction, then we can determine its rate law based on its molecularity. So if it's unimolecular, bimolecular, or termolecular, we can then determine the rate law. Okay? And it's quite straightforward. So rate equals K multiplied by the concentration of those reagents. And if there's a coefficient, then we raise it to the coefficient. This is going right back to the start of the lecture now. Now the rate of the overall reaction is going to be equal to the rate of the slowest step. Okay, so the elementary step that is the slowest will be the rate determining step, and this governs the overall rate of the reaction. Let's have a look at this one. So the experiment predicts that this is a second order reaction for NO2 and zero order for CO. Can we propose a mechanism for this? Right. So if the overall was an NO2 plus CO, that gives us NO plus CO2. Let's have a look at what the mechanism might be, because it's second order in NO2 and zero order for CO. Okay, so what that must mean is that perhaps two NO2 molecules are first reacting, and that's going to be the slow step, and then, well, it's going to be zero order for CO because that's the fast step. And because it's the fast step, the concentration of CO in solution isn't going to affect the overall reaction rate. Okay, so the rate law for the rate determining step of the following reaction, so rate equals K1 multiplied by the concentration of NO2 squared, because it's second order in NO2. It's zero order for CO, so we don't actually include that in the rate law. We can see that step 1 is our rate determining step. It's our bimolecular step as well. All right, so finally a concept check. Which of the following proposed reaction mechanisms for the reaction below could be valid? And explain. We've got our choices, 1, 2 or 3. Now the overall reaction is 2CO plus O2 gives us 2CO2. Okay. First of all, let's have a look and see whether all of these make sense from a valence standpoint. Now the one that seems odd to me is number 3, where we've got C2O, and I'm not sure if C2O would have a particularly stable Lewis structure. And the other thing is, if we were to combine those two steps, those two elementary steps, I think that we wouldn't arrive at the overall reaction, because it looks like we've got 2 oxygen atoms there on the right hand side that aren't accounted for. They're not going to be able to be cancelled out with anything on the left hand side. Number 1 seems like it might make sense. So we've got some CO plus O2 gives us CO2 plus O, and then we've got that oxygen that's produced, that single oxygen, O plus CO gives us CO2. And overall, that's going to be 2 CO2 plus an O2 gives us 2 CO2. So that makes sense. So number 1 makes sense. We can cancel out our oxygens. Number 2, does this one make sense? Let's just check this. So 2CO, okay, that adds up, gives us CO2 plus a carbon, and then that carbon then can react with some O2 and give us CO2. So if we cancel out, we're going to cancel out the carbons, and we get 2CO plus O2 gives us CO2. Okay, so that one makes sense as well. It's just number 3 doesn't quite add up. So at the moment we think number 1 and number 2 could be valid. Is there any more information? If we know that the overall rate law was the rate is equal to the rate constant multiplied by the concentration of CO squared, does this correlate with your choice in part A? So choosing between either 1 or 2, well, it must be number 2, because in number 2 we've got now our rate limiting step could be the first step, where we've got 2 carbon monoxides reacting together, and this could be our rate limiting step. And then if it's zero order in respect to the oxygen, then that's going to make sense. So that means that our choice must have been 2. The answer must have been 2.